There are common acids in there, some common acids that are really very acidic, like paratoluene sulfonic acid. We will talk about this. Paratoluene sulfonic acid is made up of the TS group. The TS group is this. This is the TS. It's TS is toluene sulfonic TS. So this is basically the T, and this is the S. So you abbreviate it as TS over there. And then the O is this O, and the hydrogen is your acidic hydrogen there. This paratoluene sulfonic acid is a type of organic acid that we use, and this acid is a stronger acid than H2SO4, and a stronger acid than H3PO4. We always use these acids whenever we are working with acid-base reactions. So if you see the TSOH has this structure, and this is its acidic hydrogen. Now, with respect to the bases, as I mentioned before, they can be strong and they can be neutral. Neutral bases, all bases have lone pairs. So, like for example, if I have water, water acts as a base, as a neutral base, and water acts as an acid from one of these hydrogens in there. It depends with what you are reacting it with. Ammonia, in here, it's more basic than acidic. So rarely we would find that a base would take this hydrogen in there from the ammonia, because ammonia is normally a base. But if you work with a very, very, very strong base, then this hydrogen will be acidic. Then that strong base will come and take this hydrogen out. So these are examples of neutral bases, and these are examples of strong bases. Always bases that have negative charges are strong. Bases that have zero charges, these are weak. These are weaker bases. Now, all of these bases, they should have what? A positive counter ion to balance them. So if you don't see a positive counter ion, this doesn't mean it is not there. See this table over here? Please, I want you to know these bases by name. Once we start chapter 4, you will know that a chain of 2 carbons, we call it an ethane. So this is why we use the word eth in there for 2 carbons. It comes from ethane, and oxide is from the oxygen, so it's eth oxide. A 1 carbon chain is called methane. It's called methane. So what you do is you take the A and E, so you use just the meth. It's connected to the oxygen, so it's methoxide. You start naming the positive counter ion first. This is sodium hydroxide. This is sodium amide over here. This is potassium, and then this guy over here is a carbon that is connected to 3 carbons. This is 1, this is 2 over here, and this is a 3 carbons. This is a CH, and this is an O in there. So this is how it looks like over here. See that carbon? Since this carbon is connected to 3 carbons, this is called TERT. TERT is an abbreviation for tertiary. We will hit on this in chapter 4. So in chapter 4, we will talk about tertiary carbons, secondary, and the primary carbons. So it's fine if you don't memorize the name of this one now. It's okay with me. This is lithium diisopropylamide. Now these 2 bases over here, see that base? This is a bulky base. It's a big base. And that base over here, this is again a bulky base. It is a very big base over there. So these 2 bases are big bases. The rest of the bases, these are small bases. Now, when it comes with their reactions, it really differs when you're using a big base, a bulky base, or a a small base. And we will also discuss those whenever we talk about alkyl halide reactions. Now, since I'm not showing pKb tables, I'm only showing pKa tables. You have to you have to change the bases into acids, and arrange the acids in terms of their acidity, and then reverse that for the base. Normally, stronger bases, they do have weak conjugate acids. So if the moment you know that your conjugate acid is weak, you know that your acid is strong. The pKa's normally they are very high. They are more than 12. Now, we've talked about bases, and you saw that bases have negative charges and lone pairs, but not every negative charge is a base. The exception is the halogens. Because these halogens in there, these are conjugate bases of strong acids. The stronger the acid, the weaker the conjugate base, okay? So this is the HF, I'm sorry. So that guy is gonna be HF, HCl, HBr, and HI. So the stronger basically the stronger the acid, the weaker the conjugate base. And all of these acids are strong. This is the strongest acid, but all of these acids are strong. So their conjugate bases are very weak. These conjugate bases, even though they have a negative charge, but still they are not strong. So all of these conjugate bases, they are an exception to our rule, and the rule says that normally bases that have negative charges are strong, with the exception of halogen anions, F minus, Cl minus, Br minus, I minus. These are conjugate bases of really strong acids, so they should be weak bases. There are also another type of base which is really strong, and that base is a carbon with a negative charge. So when you have a carbon with a negative charge and a lone pair, this normally we don't prefer to have a carbon with a negative charge because carbon is not electronegative, but the structure exists. And when it exists, it will be a base, and it will be a strong base. This is an example of strong base. It's but from butane. Butane is an alkane chain of 4 carbons. Okay, so you have 1, 2, 3, 4 carbons. So it's a but. You drop the A and E, so you say butyl, and then you put a YL in there. And then you name the counter ion, the positive counter ion, which is lithium. Amines, these are basically nitrogens that have lone pairs, and amines can either be amines that have CH3s over here. You can have amines that have CH2, CH3, which is an ethyl group. So this is why I'm calling it a triethylamine. This is the structure of a triethylamine. Another structure of amine is pyridine. So all of these amines in there, so I can have amines that basically have CH3s around them, ethyl groups around them, or any type of alkane chain around them. Or I can have pyridine in there. All of these are nitrogen bases. These are a neutral. These are considered to be weak bases. They are not strong bases. One of the labs that we're going to do is the synthesis of aspirin. Aspirin acts as both an acid and a base. Aspirin can act as a base from its lone pairs on the oxygen, and it can act as an acid from the acidic hydrogen next to the carboxylic acid there. So in its ionic form, normally aspirin is soluble in a bloodstream. And when it reacts with a base, it's basically deprotonated. This is when it's in ionic form. Now, when it is a protonated, this is the protonated form. It is a neutral. It is protonated form. It can pass through cell membranes and stop chemical reactions. Now, the other type of acids and bases is the Lewis acid and the Lewis base. This is the other type of acid and bases. And Lewis base, by definition, is an electron pair donor. So same thing as the definition of Bronsted and Lowry bases. Lewis bases donate electrons. Okay, so the Lewis base can be either a negative charge or lone pair. So basically all Bronsted and Lowry bases are Lewis bases. So they act as a double in there. So see over here, you do have lone pairs. See, you have a lone pair in here. So this is a Lewis base. At the same time, this guy is also Bronsted and Lowry base. Same thing over here. has a lone pair, Lewis base, or Bronsted and Lowry base. Coming to this guy over here, it doesn't have a lone pair, but it has a pi bond. So it donates electrons, can donate electron. This is also called a Lewis base there. With respect to the Lewis acid, now the Lewis acid, this is where we part from the Bronsted and Lowry acid. By definition, all Bronsted and Lowry acids are Lewis acids, but the opposite is not true. Not all Lewis acids are Bronsted and Lowry acids. Let me explain. With Bronsted and Lowry acids, we used to look at the hydrogen, okay? And we said that Bronsted and Lowry acids, they have to have a hydrogen, and the hydrogen has to be connected to an electronegative element, a partial positive charged hydrogen. This is the definition for a Bronsted and Lowry acid, where they donate a hydrogen to the base. So the Bronsted and Lowry base takes the hydrogen from the Bronsted and Lowry acid. With respect to the Lewis acid, we don't talk about hydrogens anymore. We talk about electron pair acceptor. We talk about basically acids that are electron deficient. This is what we talk about. So we talk about an acid, Na, that has an empty p orbital. So instead of having a hydrogen with a partial positive charge, you have an acid that has an empty p orbital that can accept electrons from the base. So base, the Lewis base always has to have lone pairs. The Lewis acid has an empty p orbital where the base gives its electrons to the acid. So we are in the same idea in here. The difference is the base still is the same. It has electrons, lone pairs, but the acid, instead of being a hydrogen with a partial positive, it's now having an empty p orbital, and now the base is giving its electrons to that empty p orbital in there. Let's have an example, okay? Example of Lewis acids. Now, we said that all Bronsted and Lowry acids, they are Lewis acids, because think about it. This is my water in here, okay? This oxygen is going to take electrons away from the hydrogen, making it partial positive. So now, instead of looking at the hydrogen here, I'm looking at the hydrogen being losing electrons. So now hydrogen has an empty orbital where the base can come and fill it with electrons. So water can act as a Lewis acid, and at the same time it's a Bronsted and Lowry acid. So see how the definition now changed. I'm not looking at the partial positive anymore. I'm looking at the hydrogen to see if it has an empty orbital, so that the base can come and fill it with electrons. And to have an empty orbital, it has to be connected to an electronegative element that steals its electrons. Same thing over here. So see, you have an OH next to the CH3. This oxygen is stealing electrons away from this hydrogen, making it partial positive. So now this hydrogen is electron deficient. So it will have basically an empty orbital that can accept electrons from the base. And this is actually the reaction that's happening here. The base normally gives electrons to the Lewis acid, and now instead of forming a conjugate acid and a conjugate base, you will form a complex. This is the difference between Lewis acid Lewis base reactions and the Bronsted and Lowry acid base reactions. Bronsted and Lowry acid base reactions give you conjugate acid conjugate base, but Lewis acid Lewis base reactions give you a complex in there, and the complex is basically distribution of the charges. So the base over here is going to lose the electrons to make a bond with the acid. So the acid is going to gain electrons, you represent it as a negative charge. Base loses electrons, you represent it as a positive charge. Now this depends. If your Lewis base has a negative charge, then the negative charge will end up to be neutral, 0 over here, and the positive also will be a 0 over here. So this basically depends on the charge of the acids and the bases. Now coming to the Lewis acid in here, that has an empty orbital. Okay, these are examples of Lewis acids that have empty orbitals in there. These acids, they are only Lewis acids. They cannot be Bronsted and Lowry because they don't have any hydrogen. Let's have an example. BF3. Okay, so this is BF3 over there. Why boron has an empty orbital? You do its electronic configuration. Boron is 5. So boron is 1s2, 2s2, and 2p1. You see that? Okay, K level is filled. This is the L level. The L level over here is not completely filled. The L level has empty p orbitals. Do you see them? These are my empty p orbitals over there. So this is going to make my boron electron deficient. So see, this is going to make the boron having a vacant orbital. So it's kind of like ready for any lone pairs from the base to come and fill it up. Same thing for the aluminum. Do the electronic configuration for aluminum, please. And same thing, aluminum will have an empty orbital. Same thing for zinc. Zinc is going to have an empty d orbital now. And iron is going to have an empty d orbital now because these are transition elements in there. So in case you have an empty orbital, this is the definition of a Lewis acid. So let's have here an example. Which of the following is basically a Lewis base? NH3, yes, it is a Lewis base over here because it has a lone pair. So it has a lone pair. So by definition, a Lewis base is a base that either has a lone pair or a double bond, or a pi bond, I mean. So Lewis bases and the Bronsted and Lowry bases are exactly the same. What about this alkane over here? No, it has no lone pairs. It has no hydrogens, no lone pairs in there, I'm sorry, or no pi bonds. So it is not a Lewis base. What about this hydrogen in here, this hydride? It has a negative charge in there. It does have a lone pair. So yes, this is a Lewis base. It has a lone pair. This is a triple bond. Yes, it does have 2 pi bonds in there. So yes, it is a Lewis base. It has 2 pi bonds. 1 pi bond is more than enough, but this one here has 2 pi bonds. So yes, it is a Lewis base. So by definition, a Lewis base has to have either lone pairs or a pi bond. Same definition as the Bronsted and Lowry bases. So all Lewis bases are Bronsted and Lowry bases. Okay, now which of the following is a Lewis acid? BBr3 over there, yes, this is a Lewis base, or a Lewis acid, I'm sorry, because the boron here in this case, it does have an unfilled valence shell. So the B has unfilled valence shell. With respect to the CH33 carbon positive, so notice here what I have here. I have my CH3, my CH3, my CH3. This is my positive charged carbon. What's the hybridization of this carbon? This carbon is an sp2 hybridization. So this is going to leave this carbon having an empty p orbital. Do you see it? This is going to be an empty p orbital. This is my orbital in there. So it has an unfilled valence shell on the carbon. It does have an unfilled p orbital on the carbon. So this structure here is going to be, yes, this carbocation. Yes, it is going to be my Lewis acid in this case. The Br negative, no, because it has lone pairs and a negative charge. So the Br negative, there is basically no unfilled valence shell in here. There is no hydrogen because Lewis acids also, they can have hydrogens. So no, this is going to be a Lewis base and not a Lewis acid. Coming to this one over here, to the alcohol, yes, it is a Lewis acid. Why it is a Lewis acid? It is a Lewis acid because, let's apply the definition for the Lewis acid, where the hydrogen, where basically the more electronegative element is gonna pull electrons away from the hydrogen, leaving it partial positive. This is gonna have a an electron deficient p or an electron deficient orbital in there that needs electrons. So yes, this guy over here is going to be a Lewis acid, and the reason why it's a Lewis acid because it contains an electron deficient hydrogen. See, I no longer said it contains a hydrogen. No, it contains an electron deficient hydrogen. This is the definition for a Lewis acid. Which of the following is Lewis acid? H3O plus. I'm sorry. Which of the following is a Lewis acid? Bronzed and lauric acid, both or neither. So I'm looking for both of those. So if you need to write down the Lewis structure for them. Okay. The moment you see an acid having a hydrogen, it can act as both. It can act as a Lewis acid and a Bronzed and lauric acid. It's a Bronzed and lauric acid because it has a partial positive hydrogen. It is a Lewis acid because that hydrogen contains an electron this contains an electron deficient site or an electron deficient hydrogen. This is why it is a Lewis acid. Cl3C. This is a carbocation, and that carbocation in here has an unfilled valence shell because that carbon is an sp2 hybridization. It has an empty orbital, so this is the same as that. So it's going to act as a Lewis acid only. It is not a Bronzed and lauric acid because it doesn't have a hydrogen to be a Bronzed and lauric acid. Same thing over here. This is only a Lewis acid, again, because of the boron. So C is the same as A. It has an unfilled valence shell. Now this one over here, no, it's neither, because first of all, it doesn't have a hydrogen for the Bronzed and lauric acid, and the boron has no unfilled valence shell because the boron is connected to 4 fluorine, so the hybridization of this guy is going to be sp3. So there is no empty orbital or anything like that for the boron. All the orbitals are hybridized in this case, so there is no unfilled valence shell for the Lewis acid. When we work with the Lewis acid base reactions, as I mentioned, your arrow always starts from the base. Base should have electrons, and the arrow is going to go immediately towards, immediately towards the electron deficient site. The electron deficient site here is the boron, so the arrows is going to go from the lone pair to the boron. There is no leaving a group in this case, so I'm going to form a complex. Electrons are added to the boron, so the boron now is going to have more electrons, so I'm going to represent this by a negative. Oxygen lost electrons, I'm going to represent this as a positive. This is called a Lewis acid base complex. Okay, it's called a Lewis acid base complex. Another example, instead of a diethyl ether, I'm using water. Same idea. This is going to be my Lewis base. This is going to be my Lewis acid from the boron. See how my arrow is from the more to the less. This is my nucleophile. This is my electrophile over here. Arrow always goes from the nucleophile to the electrophile. You make a complex in there. So arrows always go from the nucleophile to the electrophile in there. And this is most of the organic reactions. If you understand this part, that most of these reactions form between a nucleophile and an electrophile, and arrow should always start from the site that has more electrons towards the site that has less electrons in there. These are different cases over here. The electrophile can be basically the electrophile can be either a positive charge or it can be a hydrogen, whatever you want. So if the electrophile is a positive charge, this is definitely a Lewis acid. If the electrophile is a hydrogen, then that can be a Lewis acid or a Bronzed and lauric acid. Your arrow is always going to be from the nucleophile towards the electrophile. See how I'm doing it? From the nucleophile towards the electrophile, you're going to make a complex in this case. from the nucleophile towards the electrophile. You're going to make a complex. From the nucleophile, this example over here is both. Either you can label it as a Bronson and Lowry acid and base. This is going to be the Bronson and Lowry base. This is going to be the Bronson and Lowry acid. Or this is going to be the Lewis base. This is going to be the Lewis acid, whatever you want. In either cases, you're forming a conjugate acid and a conjugate base in this case. Okay. So always keep in mind, whenever you have an alkene in there, the alkene is a nucleophile. It has electrons because with the alkene, remember that carbon double bond carbon is basically a carbon that has two p orbitals that overlap with each other, and each p orbital has electrons. So these two, they overlap with each other and make the pi bond. So when I break the pi bond, when I break it, I'm losing these two electrons to form a new bond with the hydrogen. So my arrow basically is going to be when I am reacting an alkene or a triple bond with a hydrogen, with a partial positive site. It doesn't matter. It can be either a hydrogen or a carbocation, carbon positive. It really doesn't matter. Then the double bond is going to break. This is your nucleophile. Your arrow always starts from the nucleophile towards the electrophile. The electrophile here is the hydrogen because chlorine is partial negative. So it's going to open up, pick up this hydrogen. So now I broke that pi bond. One of these carbons took the hydrogen. The other one is going to be positive. It's going to be a carbocation in that case. This is the last slide. Let's go ahead and label both Lewis acid, Lewis base, draw a curved arrow. So we're going to start with this guy over here. It's going to be my Lewis acid. This is going to be my electron deficient site over here. This is going to be my Lewis base. This is my Lewis acid. So the arrow is starting always from the base, from the nucleophile, towards the boron, which has an empty p orbital in here. This is my electron deficient site. So I'm going to form basically a complex in this case. The boron is going to gain electrons. I'm going to have a fluorine in here. I'm going to have a fluorine in here. I'm going to have a fluorine in there. And then it's going to make a bond with the oxygen. The oxygen is going to basically lose electrons. So I'm going to have a CH3 over here. I'm going to have a CH3 over there. And anyways, I know that when oxygen has a 3 bonds and the lone pair, it is a positive charge. This is going to be my Lewis acid. This is going to be my Lewis base. The Lewis acid always has an electrophilic site. So my arrow is going to be from the nucleophile, from the Lewis base, towards the positive charge. So my product is going to look like, so here you go, just going to write it like this, and we're going to have an OH over here. See that OH? This is my OH. Now, what are the charges over here? I don't have any charges because, see, that base had already a negative charge. It was already gaining electrons. It lost 2 of its electrons, so it became a 0 charge. Oxygen, when it has 2 bonds, it's a 0 charge. And this carbon over here was already losing, and I added 2 electrons to it, so now it is a 0 charge over there. Don't forget that the carbon, to be positive, it needs to have 3 bonds. So there should be a hydrogen over here, but I am writing the skeletal form. So this is going to be my product over there. As I mentioned before, please remember that for every negative counter ion, there is a positive one to balance it. So the charges here are 0. This means this needs to be 0. Charges here are 0. The product has to be 0. The charge of the product has to follow that of the reactants. So now the same thing over here. This is going to be my Lewis acid. This is going to be my Lewis base. So my arrow is going to go towards the boron there. And I'm forming a complex between the boron. I have the BRs, the 3 BRs over here. Now boron is going to gain electron now because it was 0 charge. And oxygen is going to lose electrons, so it's going to be a positive charge in this case. zero charge, zero charge. Here, this is going to be my Lewis base because of the lone pairs on the oxygen, and the aluminum chloride, this is the aluminum chloride over here, is my and the aluminum chloride is my Lewis acid. This is my aluminum chloride. So basically the lone pairs are going to come, they're going to attack the aluminum, and you're going to make your complex in this case. So here you go. Your product is going to look basically like this. So you have your lone pairs. It's going to be a double bond over here. This is an oxygen. Okay, and then next to the oxygen I do have the aluminum. I have a chlorine here, I have a chlorine here, and I have a chlorine in there. The oxygen basically lost electrons and the aluminum gained electrons. Same idea over here. This is going to be my Lewis base. This is going to be my Lewis acid. The Lewis acid is basically now going to be from the oxygen. Pay attention. It is going to be from the hydrogen since I have a hydrogen. So now it also can act as a Bronsted and Lowry acid base acid reaction. So this is gonna the base is gonna attack the hydrogen and the whole thing is gonna leave, and I'm gonna end up getting my, this is called the protonation, by the way. You are protonating the oxygen and adding a hydrogen to it. So you're gonna end up having this plus of course water over there. So you're going to end up basically getting your product. If you are, this is the same as the Bronsted and Lowry base, and this is the Bronsted and Lowry acid, then this is going to be the conjugate acid, and this is going to be the conjugate base over there. Okay, so this is the end of the of chapter 2.